All right. So let's look at some examples of computing work. So here we have an example where a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is required then to stretch it an additional 3 centimeters? Right? So what we sort of have here, if you want to look at a picture for this maybe, is that one way we can imagine it is, let's say we have a block here, just as a handle. We're not going to do any masses on this, right? And let's say, here is our spring, and let's say that's in its natural length, right? So this right here, this is its natural length of 10 centimeters. So what we're actually going to do is call, maybe I should put it right here. We're going to call this point right here, this is what we're going to call 0. Okay? Because when we're dealing with spring problems, we want to measure things in terms of how much it's stretched or compressed, right? We don't want to sort of measure, we don't want to take into account the length of that spring, right? So this is going to be our 0 here, all right? And then what we're sort of looking at is saying, all right, well, this spring, has been stretched from 0. Let's see, if we're stretching it from 10 centimeters to 15 centimeters, we're stretching it an extra 5 centimeters. Right, so we want to stretch it to here, right? All right. So we know this information. We know that it takes 40 newtons of force to stretch it this far. So using Hooke's law, if we input this information, we can find the spring constant. That's the first thing we need here. Okay. So K is going to be 40 newtons over 5 centimeters. Now we want to get this in SI units, in standard units. So this will be 40 newtons over 0.05 meters. Okay. So this is 800 newtons per meter. Okay. That's our spring constant. Now that we have that, we're saying, well, let's stretch it 3 more centimeters. What happens? Right? So if I change this is in centimeters, I should really write these in meters. All right. So we shouldn't really use 5 centimeters here. We should think of this as 0.5 meters. All right, so I want to know if I stretch this, an extra 3 centimeters, so I go from 0.05 to 0.08, what happens? So the work done will be the integral of, let's see, we have 800 K, 800X. And here we're stretching the spring from 0.05 meters to 0.08 meters. Right? And the output of this is going to be the work required. Right? And again, remember, this is going to measure in joules. Right? So we do our normal business here. This is 400 x squared from 0.05 to 0.08. Right? So this part of the computation isn't terribly exciting. So let's just go ahead and use a calculator on this real quick. Where did there it is. All right, so let's see, 0.08 squared minus 0.05 squared That's 0.0039. Right, and multiply that by 400, and we have 1.56. And again, this is in joules. Right, so that's how much work is required, 1.56 joules. Right. Okay. So hopefully that wasn't too bad. Again, we just have to sort of look at how things are going. Now let's do one more problem here. Here we have a 200-pound cable, is 100 feet long, and it hangs vertically from the top of a tall building. How much work is required to lift this cable all the way to the top? So when we're looking at a problem like this, we want to, there's no sort of formula to use in this one. So we want to try and sort of set up the situation. So let's say here's some really tall building, right? So here is, I'm just going to write building. All right, whatever. Here's our building. And our cable, right? Let's say our cable is hanging from here. Please change color. Our cable is hanging from here down, 100 feet, right? So what we want to do is we can still sort of figure out what's going on here, right? So what I'm going to do here is, since we're trying to pull the cable all the way up here, I'm going to call this 0. And then down here at the bottom of the cable, that's 100, right? And so let's say, let's say we had just a mass at the end of a rope here. Or sorry, let's say we just had like, a book or something that we want to pick up and put on a table. How much work is required to do that? Well, again, it's force times distance. In this case, the force is the force due to gravity. In other words, the weight of the object. So to figure out how much work is done, we need to take the weight of the object times how high we have to lift it. Right? So here, to figure that out in this situation, what we need to do is take this cable and we want to cut it into a bunch of tiny pieces. All right? So we're going to take this cable and cut it into a bunch of pieces. Right? And each piece here, we're going to give a width or a length of delta x. Okay? And then somewhere in here, you can take anywhere along this length of cable, we're going to take a sample value. Right? And we're going to say, all right, that small section of the cable, this is how far we have to pull it up the building. Okay. So, let's see here. So this 200-pound cable divided by 100 feet, this says this cable is 2 pounds per foot. All right, so each foot of this cable weighs 2 pounds, is what this is saying. Right? So, to get the weight of this segment right here, we take 2 pounds per foot and we multiply it by delta x, and this is going to be the weight of each segment. Okay? Then, now that we have that, what we need to do is say, all right, well, each of those segments, we're going to pull it up to the top of the building, and that distance we pull it up is approximately just xi star here. So 2 delta x times xi star, this equals the work required to lift the segment to the top. right? And then we have to do this for each segment, right? So, you know, the work overall is going to be approximately, again, this is all an approximation here, the sum from I equals 1 to n, you know, n being the number of segments we cut this into, of 2 delta x times xi star. So, again, you might see where this is going. This is turned into a Riemann sum, which means the exact work is going to be the integral of 2x delta x, right? So, or sorry, dx. The delta x turns into the dx, the 2xi star turns into the 2x here. And what are the bounds? Well, the bounds are what's the smallest distance I pull up, all the way to what's the largest distance I have to pull up. So it's from 0 to 100, right? And so, you know, putting that all together, we have 0 to 100 here. And so this is 10,000. In this case, the units on this are going to be foot-pounds, right? Because these are imperial units here, right? So hopefully that all makes sense and it's not too bad. So often, you know, you'll have to sort of make these little, you know, build up these integrals situation by situation. All right. So we'll do one more example in the next video, and then that'll be it for our section on work.